So we're looking at example 2. Example 2 is pinned at the bottom, pinned on top, but of course the top is allowed to move in the vertical plane, well, vertical up and down, but the end is pinned. Right, so because we have this pin boundary condition, we need to actually physically make a hinge. Right, so unlike before where we was able to just fix the bottom face, now we need to actually put a pin. So for that, you could just include a sketch of a hole on this extrude cut. Right, so this is a 10 millimeter diameter hole. Now our 2.2 meters started at the bottom here till the top. So when we actually put the hinge here now, what we are saying is that analytically, our 2.2 meters will be actually be less than that because now we are off by 6 millimeters. Right, so it's a small change, but hopefully it will not affect the overall answer as much. Right, to correct this, what we could do, we could actually extend this by 6 millimeters and bring down the hole so that you will have from the center to the top is 2.2 meters. Right, so I'll go straight to the model. Now what we are doing is a new study. We are doing a static study. Right, because we already done the buckling. Now we're going to do a static study because we're just looking at pure stresses. Right, so I already did most of it here. Right, so our material will be the same material we had used before. In terms of our fixtures now we could actually put now this hinge. Right, so on the fixed hinge, you'll actually specify the face inside here. Right, so it will be like that. The next thing we want to do is have the top now. The top face must be able free to rotate, free to move down and up, but it must be fixed in what we have here, the Z and the X directions. Right, so what we will do, we go fixed constraint, right? We will select flat surfaces. We select the face on top. Right, and if you look at the video here, the little video here, you would see that what the symbol here represents. So ideally we want to fix in this, but we wanted to be able to move back and forth. So what we do here, we come down to translations, and we set the respective symbol to 0 because we want the displacement to be 0. Right, so 0 up and down. And then what we wanted now, the perpendicular direction to the face, we want that to remain unknown or unchanged. So we do not select it. When you click on the radio button here, you could see you unselect it. You click it back, you could specify our displacement here, but we have it as 0. Right, so this one here remains grayed out, so you don't click this here. So we telling SolidWorks that it's free to move up and down, but fixed in this direction and that direction. Right, in terms of forces, now we know that the force is 500 Newton per meter, but we cannot enter a uniformly distributed load like that. When we click on our face, we need to put the total load on the face, and then SolidWorks will automatically work out what is the distributed load. So in this case here, it will be 500 multiplied by the length, which is 2.2. That gives us 1100 newtons. So that is the force, the total force on the entire face. Right, and that works out to be 500 newton per meter. The next force we apply on the top surface here, and that is 100,000 newtons. So that is the vertical force. Right, then we mesh. Next step now, we right click and we click run. Right, so I already run and already have the solution here. So the first thing will show up is your von Mises stresses. So what we are interested in, the stress along the length of the beam. Right, traditionally it's called our sigma x, but we want the axial stress. So in this case here, that is in the y direction. So we right click and we look for define stress plot, and we look for sigma y, normal stress. Right? We talk about automatic shift. So this is our stress. So you notice the entire thing is green, meaning that is more or less around the same value throughout the beam. We have these peaks here again because now of the non-ideal situation where we have the hinge. Right, so we'll be interested in the maximum stress which we predict is at the center. So in order to get a value of the center, what we could do is we could go on right click again, we could click on probe. So we want to get the stress at a node, a specific point. Right, so we click on um, selected entity, so we click on one of the lines here. Right, so ideally we know we're asking for the stresses along this entire line. We update. So you can see all the node numbers for all the nodes that comes down on line, and we have a value of stress. Right, we have the x, y, and z location. So of course is the x location is 50, y, and z. Right, so the y location, that is the vertical location, well the top is 200 millimeters, that's the length of the beam. So we're looking at the middle is where we expect to get our maximum stress. So the middle would be, of course, 1100. So we scroll all the way down here, and we look for 1100. Right, so when you click on 1100, you would see here that node, 1100 is the location. The stress is minus 6.7 by 10 to the power 7, which is minus 67.6 megapascals. And our value for stress that we got was 67.8 megapascals. So you can see the analytical solution is extremely close to the finite element solution, and vice versa. Right, so this is one way of validating or doing a pre-analysis. Again, this is how you do your pre-analysis. So when you actually get this on, now you could go ahead and modify your column to be whatever complicated shape you may have in your analysis. Right, so the next step now is to check displacement, maximum displacement. So we come define displacement plot. Right, so we're looking for your displacement in the z direction. So we could see the maximum, of course, will be the dark blue in the middle here, which is minus 2.735 millimeters, and our calculation, we actually got about 2.8. Right, MATLAB gave 2.8, but if it is you increase the amount of decimal places, in MATLAB you might actually get 2.78 something or whatever. Right, so 2.7, 2.8 millimeters. So again, we validated the displacement side of things here. If visually we want to see how the displacement looks, we could come here and select edit definition, and our deform shape, we could actually click that radio button. So what we are saying is that we want SolidWorks to magnify the deflection or the deform shape by about 80.4. Right, is just a scale factor. It exaggerates the deflection so we could visualize it, and that's what it does here. So this shape now obviously would follow our mode shape, which is in the cos sense. Right, now if you were to plot this deflection at every point, we are supposed to be able to get back that deflection equation that we defined in the notes for V. Right, so if you go to page 28 of the notes, we have V is equal to a whole long equation. So that equation for V is supposed to correspond to the V over here. So if you were to plot a finite element versus analytical, they're supposed to have a very small error, because we saw how good the maximum correlated with what we actually calculated. Right, so what you could do as an exercise, separate, I mean not for marks or anything, but you could right click probe, displacement here, selected entities. So again, we select in this line, update, and we would get all the displacements in the z direction along all the different nodes here. Alright, just as a check, you can look at y is equal to 1100, again, which is the middle point of the beam. And we could see that minus 2.732, which is what we expected to be around our maximum. Right, remember, it may not be exact point. It have 3.2 and the maximum here is 3.5, and again, that's because 1100 millimeters is not the exact center because we had the whole hinge at the bottom. Right, so anyway, what I wanted to show here is that you could come on the bottom here and click plot. So you could actually plot the curve. So what we did, we plotted the distance for the entire beam here. Right, this is a parametric distance. What this means is that at point 8, multiply point 8 by 2.2 to get what is the distance in meters. Right, 1 really here is 2.2. 0.4 multiplied by 2.2 will give you this distance here along the beam. Right, so this is how the plot will look. You could also export the data here. Right, so to our CSV files, our CSV file you could plot in Excel, and you could actually plot now those results from the final element versus the equation V that is given in the notes on page 28. So you could actually plot those two graphs and actually compare now analytical solution versus finite element solution. And again, that is a pre-analysis, that is a form of validating your finite element model. Okay, so some other things you could do is in your MATLAB script, well, the nice thing about having a MATLAB script, you could just change the values. So you could change the values of P, you could change the values of W, you could make P0 and verify the answer. You can make and then do the corresponding change here, and so all these different ways of validating and making sure that forces have a proper effect you could do. So for example, we could suppress this, right click and run. I'd say note what's something here. So with that force suppress, all we have is a uniformly distributed load. So you could see here that we have bending stress. So we have the zero, almost zero in the middle here, very small, shows that that is the neutral axis. And then it goes to the really higher values. Right, so if you make P equal to 0 in your uh, um, MATLAB script, then again you could come and check the corresponding values here. Right, so 1100 is what we're looking for. And so that's our value of stress, minus 14.4 megapascals. And then you could verify that in your MATLAB script. Right, so in my MATLAB script, I actually got minus 14.5. Here's minus 14.4 megapascals. So again, it's very close. Now, in your MATLAB script, if you were to make P equal to 0, so if you look at the equations, right, if we just revisit the equations for the stress and for the displacement and stuff, you'll notice that we have P in the denominators. And if P is 0, therefore we will have infinite, or MATLAB will give an error, not a number. So what you need to do is instead of making P equal to 0, make it 0.1 or 1 Newton. Make it a very small value so that numerically you would not get that infinity issue.